Hello and welcome to the final submodule in this introductory slide set. And here I want to talk about future trends and issues. Very specifically, I want to talk about the increased cost of custom fab, particularly the NRE, that is the upfront design and mask making aspects. As a general trend, the cost to the first chip is rising about 60% with every generation, and it's going to be very substantial. This consists of two parts: the design cost, which we'll talk about in a couple of pages, and mask making, which today in an advanced process can be $4 million or more. Of course, globalization has affected this industry a lot. One aspect of that is increased time to market pressures. That is to shorten the design cycle, or shorten the design time, so the product can be released earlier than that of your competitors. This creates acute issues because it's fighting against the next point, which is the increased complexity of the design. Because the number of gates are going up, because the impact of interconnect is increasing, because the impact of process variations, that is, the variation in performance between different implementations and different transistors is increasing. And because we're having to deal with sub-wavelength lithography, that is, the masks are made with 10 nanometer scale features in them, but are imaged using 192 nanometer light. This means the masks can't just be simple photo masks corresponding to the pattern you want to see on the chip surface. They have to be a optically corrected mask to take account of the refraction of the light around the sub-wavelength mask features. And this leads to enormous complications. So the complexity of design is getting larger, which of course is why the design cost is getting larger, but at the same time there's pressure to reduce design time. So these are the trends that we're seeing in response to these issues. Of course, there's increased use of FPGA and gate arrays. As the cost to first silicon goes up for standard cell designs, there's fewer and fewer markets that benefit from that large investment that is required. In general, to do a large, complex, modern process, standard cell design, you need to be addressing $1 billion market. There's increased use of platform solutions. That is, each generation of the design is based off of a common platform, and that platform has a multi-core CPU unit and ASIC accelerators. And I'll illustrate this in a little while. There's increased use of existing designs, whether these are designs are evolutions or previous designs in-house, or designs that are purchased from third-party vendors who make such things. These existing designs, which are typically at the RTL level, are referred to as IP, or intellectual property. There's increased use of system-level modeling tools. Part of this is to try to get everything right early. For example, integrate a hardware description in system C, that is above the RTL level, together with a C-level description of the code running on the embedded processors, and at the system design phase, verify that they'll run together correctly. Of course, what is called performance verification and logic verification are seeing more and more design effort going into them. Logic verification, because as the number of transistors go up, the verification effort goes up, and using IP actually doesn't help much here because you still have to verify that IP works correctly with the rest of the chip. Performance verification really means that the chip will run properly at speed without logical errors. And because of scaling, both of these are getting much more complex. But the performance aspect, because of increased process variations and the complexities in the mask layouts introduced by sub-wavelength lithography. So put this together, for standard cell design, the cost of first silicon is getting so high that you must be addressing a large addressable market, typically $1 billion or more, to justify the sort of costs we'll see in a moment. And also the product risk must be low. you can't. It's you're much more likely to see speculation on products. Again, particularly when you're dealing with these advanced nodes. I'm going to be a little careful in this set of slides. Most of what I'll be talking about here is when you're doing a leading edge product, trying to leverage Moore's law into an advanced node. There actually are a substantial number of products designed or even redesigned using what are called quote-unquote legacy nodes. That is older technologies such as 90 nanometer or 130 nanometer, where the product can benefit from that older node, which is much cheaper to design for, doesn't need the advanced features in the modern node, and can be cost competitive using that platform. That's just a side issue. I'll never ask an exam question about that. So this slide illustrates the trend in design cost as we go to more advanced process nodes. You can see this is predicting that a substantial ASIC done in a 22 nanometer node will cost $50 million to design. And as you can see here, though the architecture and physical design, and I think architecture here includes logic design, does increase with the node, because of IP reuse, it doesn't increase dramatically. What increases dramatically is logic verification, the top bar, and performance validation. That's what I believe they mean here by validation, the middle bar. And the cost of doing this is increasing very dramatically due to the complexity issues described a couple of slides ago. As I said, another trend is towards platform-based designs, also referred to as a system on a chip. This is a generic example of a system on a chip. Here we have 4 cores, possibly more. We have accelerator engines on the bottom left. We have a standardized, most probably reused IP, switch fabric that can connect these together and provide data communications across them. We have the bottom right, high-speed connectivity to off-chip structures. These are usually custom ASIC designs. And of course we have a memory hierarchy, particularly in this case a shared L3 cache, and of course a memory interface to DRAMs and flash memories. And you see, most of this is standardized, and a lot of it doesn't change from generation to generation, except of course it gets smaller and faster, and you have more of them. Add more cores, add more accelerators, scale up the non-blocking switch fabric, scale up the speeds of the interfaces and the sizes of the memories. So here's an example. This is a mobile system on a chip. Here we have a single core design. Of course, now they're going to 4 or 8 cores. And we have a number of accelerators, a graphics accelerator, an image processor for the camera, a video processor for the video camera that's integrated into the phone, a number of interfaces down the bottom there. For example, mobile DDR is the interface to the DRAM memory. NAND flash is the interface to the NAND flash. I2C refers to a particular communications protocol used to integrate with sensors. Most probably here the MEMS sensors for detecting motion. Right. And you can see these are integrated together onto this system on a chip, called as such because it is quite a complex system, more complex than the Saturn rocket on this particular chip. One of the aspects I mentioned that makes this harder is that the impact of wiring increases with each generation. I illustrate that at the top of this slide. I ask you this question. If you take wires with a certain type of cross-section, as shown on the top left, and shrink all the dimensions in the cross-section uniformly, what happens to the capacitance per unit length? Capacitance per unit length stays the same. It does not depend on the actual dimensions, it depends on the ratios of the dimensions. Think of a unit capacitor equation. The capacitance is proportional to the area of the distance between the plates. Well, if you shrink both the area and the distance between the plates proportionally, it stays the same. So the capacitance stays the same, but what does change as you shrink the wires? The resistance goes higher. So the RC delay gets worse, the RC delay per unit length. Thus, the gates are getting faster, the wires are getting slower. One solution to this, as inferred in the third graph from the left, is to insert buffers into the wires in order to keep the speeds up. And as we go to more and more advanced nodes, we have to put a lot of buffers into the wires to try to keep their speeds up. In addition, we add wiring layers, as on the right-hand side. And on the second graph there, we have to spend more and more power driving the wires as a percentage of the total power of the chip. This number here is a little bit high. It's typically more around 40% today. There's one other issue I want to talk about before closing this set of notes, and that is employment growth. Actually, this area is quite robust and has been for a number of years. There's actually quite a strong demand for digital designers and verification engineers, and that will continue well past the end of the exponential stage of Moore's law. This was a survey done by Electronic Design News, a magazine, on skills needed to get ahead in their professions, a survey of engineers. And you can see here the top of the ranking, at least in North America, was digital design skills, which is what this class is about, and it's what ASIC design is about. You might notice that IC design skills are at the bottom there, near the bottom there. I think that actually refers specifically to layout, which is not normally a function done by engineers with a graduate degree. Though a little dated, this is a table describing engineer hours to design 1 million logic transistors versus the technology node. And what's interesting is the trend in the percentages on the right-hand side. And though more hours are needed per million logic transistors for all the stages of design, you notice the largest area of growth is the specification stage. This is the architecture, the definition, the hardware-software co-simulation that happens up front in the design. And to me, this is interesting because this is also a growth area for you once you go out in the profession. You'll most surely start in logic design or validation. Validation is also verification here. But I encourage you to learn a lot about system functions, learn a lot about the applications, and get a broad perspective on chip design so you can move up to the specification stage. I suggest you try to seek the title of system engineer or architect or consulting engineer. It's called different things in different companies. These are the senior technical ranks that actually specify what the next generation of products are looking like. So that brings me to the end of this introductory section and the last submodule within it. This slide is meant to remind you of the major points of this section as a whole, not just this submodule. First of all, Moore's law is an exponential scaling law. Very specifically, the number of transistors per chip scales exponentially. This means the performance of a chip scales exponentially from generation to generation at the same cost, and the speed also gets faster, which further increases the performance. This has profound implications on digital products. Imagine what this would be in other sectors. Imagine if your automobile, and I'm not going to tell you that same joke again, but imagine if your automobile was on the same exponential scaling curve. How often would you buy a new car? Well, you might buy one about as frequently as you buy a new cell phone, which is mostly about every 2 years. Why do you buy a new cell phone every 2 years? Because that's about the design cycle at which those digital chips in there move to a more advanced process and have more stuff on them that you want. And this is true of many digital design areas. Networking, we've got to keep adding more capacity so people can do video. Computing, we are obviously continually adding more capability to our computers, making them faster and more responsive and more overly useful. And you in your lifetime have seen many products that are on a 2 to 5 year cycle in terms of profound new capabilities, each generation of that cycle. And remember, someone has to design all those capabilities on this fast escalating curve. Second major point, we talked about the different ways in which ASICs are implemented: standard cell, gate array, and FPGA. RTL is the entry point for all of them. And the choice between the implementation style is driven by the performance and power requirements of the end product, and to what extent the large NREs of standard cell can be justified by the market. And you've already done a quiz on this to give examples of where products fit in, and I hope you're starting to get an idea of how this works out. Many CAD tools are used in the design process, and here I break them into the major groupings: logic simulation and synthesis, which of course is what this class is about; place and route to produce masks; all the verification, including back annotated timing verification from the place and route, because those wires have such a big impact on timing and performance; and all the things that go into verifying the mask sets before they can go out to fabrication. And finally, standard cell design cost increases dramatically at the advanced nodes, going up 60% of generation due to all that complexity of the large number of gates. You talk about 1 billion logic gates. The large process variations make it much harder to get the timing right. The complications that come in because of subweighting of lithography. And how are we addressing these? We have platforms that evolve, and with each generation we reuse IP from previous generations. For example, why change the codec for a camera except to compensate for the increased number of pixels? And we also try to go design management styles that speed up the design process. For example, spiral design, which refers to doing all the activities involved in the chip design at the same time, rather than the simpler approach of what's called waterfall design, where you do one stage of the chip design, hand it off to the next team, and so on. Well, I hope you've enjoyed this introductory section. I now encourage you to do the homework, quote unquote, associated with this section, and I hope you got a lot out of this. If you've got any questions, of course, please ask in the forum, or for students at NC State, ask me in class. Thank you very much.